Hi, this is Dr. John Bergduff. You might notice for this section that this is the only media in the assignment. That is because this particular section is a study of roots of all different kinds, and we are only going to focus on square roots for the time being. There are also such things as cube roots and fourth roots and fifth roots, and those are valuable, but we're going to study them later. So we're going to just have this one media assignment so that we can focus on just square roots. What are square roots? A square root of a real number b is a number which, when squared, that means multiplied by itself, results in b. Now that is kind of a backwards sounding definition that might be a little bit hard to follow. A square root of a number b is a number which, when you square it, you get b. Let's take a look at a simple example, and you might already notice something that looks a little odd in this question. It says, what are the square roots of 25? We'll explore that in a minute later, but let's just explore the definition for now. A square root of 25 would be a number that when you square it, you get 25. Imagine that you're trying to fill in a box, and you're asking yourself, what is it that I can square so that the result is 25? Whatever goes in that box is a square root. And then we think about it and we realize that 25 is a number we might call a perfect square because it is 5 squared. So a square root of 25 is 5. And so far so good. But again, it says square roots. That's because actually there is a second square root as well. Think about this a little bit more and think about what else you could put in that box. And you might realize that if you put a negative 5 in the box, negative 5 squared, negative 5 times itself, a negative times a negative is a positive. So negative 5 is also a square root. Now, if you've studied square roots before, that will seem strange, but that is actually true. The number 25 has two square roots, 5 and negative 5. Hold on to that for a minute if you feel uncomfortable. What are the square roots of 0? So is there a number that when you square it, when you multiply it by itself, you get 0? Well, 0 would work. 0 times 0 is 0. And I'm kind of trying to be a little tricky here because if you think about it, that is the only one. So there are two square roots of 25, but only one square root of 0. Very strange. What are the square roots of negative 16? Again, think about what can I put in the box? What can I square to get negative 16? And at first you might think, oh, that's easy. That would be negative 4. But negative 4 times itself, multiplying the entire thing, would give me positive 16. A negative times a negative is a positive, so that actually doesn't work. Well, 4 doesn't work, so we've got a little bit of a problem. What we have, in fact, is that there is no real number that will work. There is no real number that when you square it, you get negative 16. So what we're going to have to say is the square root of negative 16 is not a real number. Now later in the course, we'll explore what are called imaginary numbers. We'll find out that that gives some meaning to the idea of a square root of a negative. But we're not going to look at that quite yet. For right now, we'll simply say that a square root of a negative number is not a real number. So sometimes numbers have two square roots. Sometimes they only have one. And sometimes they don't have any that are real numbers. Depends on whether the number you're taking the square root of is positive, 0, or negative. Now, if you know a little bit about square roots already, you might be saying, well, what about this symbol? Oh, there it is. What does that mean? So looking at this symbol right here, this is associated with square roots, but it has a particular meaning. We often just say the square root of b, but actually what that symbol means is the non-negative square root of b, provided that a real number square root exists at all. Now, that's a lot of words, so a simpler way to say that is to say that the square root of b is the principal square root of b. When I see this symbol, I should say principal square root, not just square root, because many numbers have more than one. Now, that little symbol itself, that little doohickey there, has a name. It's called a radical. And we'll use that term from time to time. The symbol itself is called a radical. So let's look at some examples. The principal square root of 25. Now, again, we already noticed that 25 has two square roots, but this symbol says pick the non-negative one. So the principal square root of 25 is 5. Two square roots, but only one of them is the principal square root, the non-negative one. Now, 0 only has one square root, and it's non-negative, not negative. So the principal square root of 0 is 0. And the principal square root of negative 16, well, notice back up here I say provided a real number square root exists. There is no real number square root of negative 16. So we would just simply, all we could say is that the principal square root of negative 16 is not a real number. Pretty unsatisfying. Let's look at some other examples of principal square roots. Now, at first glance, you might look at this next one, number 7, and say, oh, look, that's also not a real number. Look at the negative sign. But look at where the negative sign is. It's not underneath the radical, it's outside. What that means is we would perform the principal square root first, and then just append a negative sign in front of it. So the only thing we're looking at a principal square root of is the 81. Now, is there a number which when you square it, you get 81? Yes, 9. Now, negative 9 would also work, but because we're talking about the principal square root, it's going to simply be 9, but appending the negative sign in the front tells me that the answer would be negative 9. Principal square root of 81 is 9, and then put a negative up front. Fractions. At first glance, it might seem that fractions are going to be a lot harder. Generally, we don't like them very much. But if we think still about the idea of what do I square to get the 4/9, and realizing that since I'm talking about a principal square root, I'm only going to take the positive results. And then you might realize, oh, that's not so bad. If you had 2 over 3, you would square 2/3 would be 2/3 times itself, and 2 times 2 is 4, and 3 times 3 is 9. That's going to lead us to a property that we're going to find very useful as we go farther along, that if you have a radical over a fraction, you can sort of split that radical and write it as the square root of 4 divided by the square root of 9, principal square root of 4 over principal square root of 9. I almost said the wrong thing myself. And then the principal square root of 4 is 2, and the principal square root of 9 is 3. The answer is 2/3. That's not so bad. Decimal. Oh boy. Okay. Now, with this decimal, unless you're going to use a calculator, and for the right now we want to resist that for a minute. To get a better understanding of this we might want to write the decimal itself as a fraction. Fractions seem harder than decimals, but when it comes to square roots, they're actually a little bit more friendly. 0.64 is read as 64/100ths. So when I see the principal square root of 0.64, I really should be thinking about the square root of 64 over 100. Oh, that's not so bad, because we can use the property we just discovered and say, well, that's the principal square root of 64 over the principal square root of 100. Is there a positive number which when you square it you get 64? 8 times 8. Is there a positive number that when you square it you get 100? 10. So this would be 8 over 10. Now I could reduce that and state that as a fraction, but since my original question was stated in terms of a decimal, let's write the answer as a decimal. 8/10 is 0.8. That's how you would want to handle a principal square root of a decimal. Write it as a fraction first, and then think about the principal square root, and then write it back as a decimal. Principal square root of 11. Okay, now we have a problem. So if I think really, really hard and try to think about, is there a number which when I square it, it gives me 11, I have a real hard time coming up with something. If I put a 9 in there, let's not do 9, that's a silly one. What I meant to say is this. If I put a 3 in there, 3 squared would give me 9. That's too small. If I put a 4 in there, 4 squared is 16. That's too big. It does seem like there should be something between 3 and 4 that when you square it you get 11, but what it is hard to say. So what we're going to do is we're going to break down and get our calculator out. You can't see me, but I'm getting my calculator out. And I noticed that there is a square root option on any calculator, and I punched that out. Square root of 11. And my calculator tells me that the principal square root of 11 is 3.3166247. Oh, no wonder I couldn't come up with that. That's a bit complicated. And in fact, this is only an approximation. This decimal pattern really continues forever and ever. And if you notice there is no logic or pattern in those numbers, it seems to continue on ad infinitum without any repeating or terminating. We have a name for that, and we're going to look at that in a minute. But to begin with, notice that some of the numbers we've looked at so far, some of the answers we've gotten so far, -9 2/3 and 0.r, those are 0.8. Those are examples of rational numbers. Rational numbers are numbers which can be written as fractions. Rational numbers have repeating or terminating decimal patterns. All of these numbers can be written as a fraction. Even like the -9, you could say that's -9 over 1. 2/3 is already written as a fraction. 0.8, we saw from the previous example 9, that's 8/10. All of these have repeating or terminating decimal patterns. You can see that in the -9, it's just -9, and 0.8 is just 0.8. If you punch in 2/3 on your calculator, you're going to get this. 2/3 equals 0.66666666. Actually, the 6's repeat over and over and over ad infinitum. That's sort of like what happened with the principal square root of 11, but this pattern never repeats. This pattern does. Rational numbers are numbers, or numbers which can be written as fractions, always have repeating patterns that terminate or repeat. Now, irrational numbers are real numbers which cannot be written as fractions. Their decimal patterns neither repeat nor terminate. So when I go back to the square root of 11, I would say that that is an irrational number. Principal square root of 11. I caught myself again. Nothing bad about that. It just doesn't turn out to be a nice rational number. Here's the deal. Any square root that is a real number but not a rational number is an irrational number. So some square roots come out very nicely, like the principal square root of 9 is 3. Others don't come out quite so nicely, but if they are real numbers and they're not rational numbers, they're going to be irrational numbers. Take a look at this. If you think for a minute, example 11, can you find a number which when you square it you get 55? And you sit and think for a minute and you realize, no, I can't. Because that's not going to be a rational number, you know right away that this will be an irrational number. And I will therefore not be able to just come up with it in my head. I'll have to use a calculator to get an approximation. So I'm going to do that. I'm going to punch into my calculator the principal square root of 55, realizing that there's a negative in front of it. The principal square root of negative 55 looks like it would be 7.416198487, and that continues on and on. Ick. Now, often what we are asked to do is to just approximate an irrational square root by rounding to a certain decimal place. Let's say I want to round that to the thousandths place. The thousandths place is right here, and the number just beyond the thousandths place is below 5, so I would round that down, and I could use this symbol here. Negative principal square root of 55, I forgot my negative sign here, notice that should be negative, will be negative, it will be, let's say that better, approximately, here's a symbol that means approximately equal to negative 7.416. This symbol here means approximately, or approximately equal. So since the irrational number has a decimal pattern that never repeats and never terminates, we'll probably just round them off to some degree and give an approximation. So some square roots will give me irrational numbers. One last set of examples before we call it quits for this video. Without using a calculator, determine between which two consecutive integers the principal square root of 17 lies. Here's another example of what would be an irrational number. There's no rational number that when you square it you get 17. But if you think about 17, the number 17, it lies between two perfect squares. The principal square root of 16 should be a little bit smaller, and the principal square root of 25 should be a little bit larger. I'm just thinking about numbers which are perfect squares. That means that the principal square root of 17 would have to lie between 4 and 5, since those principal square roots are rational numbers that we can figure out. So without using a calculator, determine between which two consecutive integers the square root of 17 lies. It lies between 4 and 5. That means that even if you don't have a calculator handy, you can at least get an idea of about where an irrational principal square root lies. In fact, if you think about the fact that 17 is much closer to 16 than it is to 25, that tells me that the square root of 17 is probably much closer to 4 than it is to 5. Let's do one more of those. This one's negative, and that's okay. We just have to remember that in negative numbers, the number that's larger in absolute value is actually farther to the left on the number line. So doing something very similar to the other one, 97, can't think of a nice rational number that when you square it you get 97. But negative the square root of 100 should be a little bit smaller than that. I'm thinking of a perfect square that's just a little bit smaller. And negative square root of 81 should be a little bit larger. Again, the negative number, negative square root of 100 is larger in absolute value. That means it's farther to the left on the number line. So the negative principal square root of 100 is less than the negative square root of 97, is less than the negative principal square root of 81, and that tells me that the negative principal square root of 97 is between negative 10 and negative 9. Try to remember that that symbol means principal square root. And you'll see in videos, and you can see how I keep forgetting myself, we get very sloppy and often just say that that's the square root. But we really shouldn't say that, because every positive real number has two square roots, and that symbol represents the non-negative one only. That's a little bit about square roots. Hope that made sense. Take care. Bye-bye.